Hello everybody, welcome to my next video on hypothesis test for the mean, population mean, with the standard deviation unknown. Since this is our third video, let's just get right to it. If you need more details, I'd watch my previous first two videos on this type of hypothesis testing. All right, what do we got here? Well, in 2010, it was reported that people who move from home to home frequently as children tend to have lower than average levels of well-being as adults. A psychologist wants to study this further and studies 42 adults who have moved more than 5 times in their lives. 42 adults. Let's start filling in the blanks. 42 adults. That's clearly my sample size. And also, let me talk about assumptions as we're doing it. I love the fact that 42 is over 30, which means I get normality and I can utilize the Z or the T distribution. So that's always in my head is assumptions are checked. Nice. What else we got? These adults were given a standardized well-being survey from which it is well documented that the average score is 40 points. So that is the average score on the standardized test. That would be the national average, mu. All right? So the national average mu is 40 points. The study produced an average of 37 points. So the 42 adults I studied, when I collected their data and averaged it out, I got 37 points with a standard deviation of 1.8. Now understand, the study produced the standard deviation. And since the study produced the standard deviation, that is a sample standard deviation. And because it's a sample standard deviation, when I do a hypothesis test, I'll be doing it with the T statistic. I need to make that very clear. Everything I do here will be T dot inverse, T dot dist, and the test statistic because that was a sample standard deviation. That's the most important point of this whole problem. Let's get to the question. Is there evidence? Well, that's a hypothesis test. If I want a confidence interval, I would say build a confidence interval. If I wanted a sample size, I'd say find the sample size. In this case, is there evidence? That's a hypothesis test. At a 10% level of significance. Well, a 10% level of significance is your alpha, 0.1. That's your level of significance. I need to know the alternative. That's in the question. It says, is the true average different from? The true average different from. That means we're looking at a two-tail. A not equal to test. Now, I've written this all down in Excel, but let us bring out our PowerPoint, our Word here, so we can check out the details written down as they should be. So first of all, they're saying the national average is 40 points. That's the information we have collected. The standardized test gives you 40 points. We believe this special group of people that move a lot, their score is going to be different from that. That's exactly what I'm testing. That's the alternative is what we're testing, where the is there evidence. People often ask, how do I know my alternative? Please read the question over and over. It says, is there evidence the score is different? That's why it's not equal to. Now you're going to list everything. You should list your alpha, your N, your X bar, your S. I have already listed them over here in Excel, but you should list them. From here, so that's your data collection point. From here, the next natural step is to build your critical region. So how does one build the critical region? Well, it is a T statistic because we said it was S. S leads us to the T statistic, okay? That's very important. The S leads us to the T statistic, sample standard deviation. I know it's not equal to because up here, remember, recall from my previous two videos, alpha and not equal to help me build this picture. The not equal to is both bars, all right? The alpha is the area outside the level of significance. The alpha was 10%, leaving me 5% on both sides. I'm doing this one faster because, again, I've had two videos. Please go back to them if I'm going too fast. Or, of course, you have the pause button at any time you'd like. So we have the T, critical region value. How does one find the T critical region value? Well, to find any T critical region value, you're going to use T dot inverse. Understand you need the area under the T value, which would be 95%. How do I know? Because there's 5% above it, so there's 95% below it. Degrees of freedom, well, that is n minus 1. And that'll find my t critical value. So let me just write that in. My critical value will be t dot inverse, and the probability below is 0.95. Degrees of freedom is n minus 1, so that'd be 41. And there is my critical value. Notice n is 42, so n minus 1 would be 41 degrees of freedom. So 1.68 is my critical value. That is this bar, 1.68. And due to symmetry, this is negative 168. And so here is the defining moment. You do not reject H naught if you fall into here. This is the quality control section. If you get into the red section, you will reject. If you get into the red section, you will reject. So let's test it out. What do I do next? Well, I'm going to need my test statistic. These are everything you should be doing when you're building the whole research. So what's our test statistic? Well, you can look it up on a formula sheet. The test statistic is x bar minus mu divided by s over radical n. At any point you're having an issue, please pause the video and check it out. Understand, I do have my PowerPoint here, and in my PDF file here, I have the formulas and details I need for this problem. I would pause, take a picture of the screen, and know what I'm working with. What I do when I'm running a lot of hypothesis tests, I always make sure I'm under the right section. I have a bunch of these sections in this pamphlet of 7 pages. Hypothesis test for average, because that's what I'm looking at, the average score, and I have the sample population that we just discussed. That's the t-stat I am building. M and x bar mean the same thing to me. All right. So let's build the test statistic, shall we? The test statistic is x bar, my average, versus the national average. But then I got to ratio it by the appropriate s over radical n. And we get negative 10.802. I'm going to pause to make sure I wrote that code correctly, because that is outstanding t-value. So let's make sure this is right. It is F48 minus F45, so 42 minus 40. That makes sense, divided by S divided by the square root, and that looks good. So yes, in this case, our test statistic is negative 10.8. The negative doesn't bother me, okay? The negative does not bother me at all. You can definitely be below average. And in fact, our score is below average. It's just amazing to me that 37, a score of 37, which is only 3 points under, has a ringing up a negative 10.8. Remember what this statistic means. It means if you do 10 jumps utilizing the sample standard deviation, which would be 1.8 divided by square root of 42, you would move down 10 points from below average. That is amazing. And so I know right away which color I want to use, green. I know right away my test statistic is well within the rejection region. All right? My number is clearly in the rejection region. So that is my first quick conclusion. My first quick conclusion is I reject H naught. And if all you were utilizing is the critical region check, you're done. This, what I just did quickly, is called the critical region test. You build a critical region based on alpha and your two-tailed. You take your test statistic and see where it falls. If it falls in the red, you reject. If it falls in the do not reject, you do not reject. In this case, we reject. All right, so we're done with the critical value approach. So sometimes people don't like the critical value approach, and instead they look at the p-value approach. So what's the p-value approach? The p-value approach I'm utilizing as a check. First, it is a not equal to test again. But now you put your number down, negative 10.8. That is your statistic. You utilize your statistic in the p-value. And of course, it's symmetric opposite because we have a two-tailed test. If this was not a two-tailed test, I would not have both bars. But it is a two-tailed test. The p-value by definition is the odds, the probability you're going to find another sample, redo this whole process, and find another sample more extreme. I.e., it is the total area outside of your test statistic. So how do I find this? Well, again, the only time I use .dist, that is norm s dist or t.dist, it's when I'm doing a p-value. Since I'm utilizing the t, I better do everything with the t.dist, and that's very important. So the p-value. The p-value will be twice because there's two regions. And since I have the negative, I'm going to utilize that to make my life easier. T.dist of the negative 10.8, comma, degrees of freedom, always, comma, 1 to do the cumulative effect. So again, t.dist, what it does is says, you give me the bar. You tell me where the bar is. I will find the area underneath it, which would be the lower red region. Degrees of freedom, remember, tells me the particular t-curve I'm doing the advanced calculus on. So that's why we need the degrees of freedom in there. But again, you give me the bar, I'll find the area below it, which is also corresponding to the probability below it. The double is because we have two sides. And that is our code for the p-value. All right, so let's put that into Excel. Excel to me is nothing more than a calculator. And that's what I use it on. 2 times t.dist. Now the x value, happen to have it there. Sweet. Degrees of freedom is n minus 1. What is that? Well, I can do this minus 1 if you like, comma 1 always. And there's our answer. And I expected a ridiculously small number. People, your t statistic is negative 10. There's not many people that can get below a negative 10. That's how many. That is 12 zeros and then a 1. A really, really small number. For all intents and purposes, that is 0. Unless you're doing something really, really strange, your p-value is 0. All right? And so what does that mean? Well, your p-value approaches, this will be less than alpha. The alpha in this case is 10%. But I want you to notice something. I don't care what alpha is. So if you change alpha to 5%, I don't care. Look at that p-value. It's 0%. Pretty much no alpha I'm going to be bigger than. And so our rule is, if my p is less than alpha, I reject h naught. That's just one of those things you flashcard until you get it in your head. If your p-value is less than alpha, you reject. If my p-value is greater than or equal to alpha, you do not reject. So again, if your p-value is less than alpha, you do reject. So in case, once more time, I do reject here. I do reject h naught. And that is the p-value approach. Some people really prefer the p-value approach because then they can look at it and go, hey, if I change alpha to 5%, it doesn't change the conclusion. I still reject. Heck, if I change it to 1%, I still reject. 0% is less than any of the convenient alphas we choose. 1, 5, or 10% that you put down. And that's why some people really like the p-value approach. So, part B here, if we change to 5%, does that change anything? The answer is no. We still reject h naught since our p-value is 0%. I mean, that's what it is. Our p-value is 0%, and that will mean we will reject no matter what alpha we change it to. So that's important for me. Cool. Now, of course, there are a couple extra pieces before I write my beautiful summary, all right? I already have my 2 tests. I've done the critical region test. I've rejected. I've done my p-value test. I've rejected. Now I can check to see if sample size had a factor. That's called the Cohen's d, okay? The Cohen's d is just a quick check to see if sample size was a factor. So I can run the Cohen's d, and that's just a formula. It is x bar minus mu over s with an absolute value on it. That's the measure for Cohen's d. It's a quick measurement to determine if sample size was a factor. If you notice, n is not part of this formula. Well, that's important, right? You want a formula that does not rely on sample size. So here we go. Absolute value, ABS. So now I need X bar minus mu. Then I need divided by S. And yes, I'll accept the double parentheses I made a mistake on. So there is the D value, 1.67. At any time, please pause the video and check out the Excel code back up here to make sure you see how I typed it in. 1.67 is my D value. What does that mean? Well, that's why I have my little articulate cheat sheet. If the D value is below 0.2, we'll have an issue with sample size. If the D value is over 0.8, we don't have an issue with sample size. And that's awesome. We do not have, so this implies there's no issue with sample size. Sometimes people think you're getting a rejection because of the sample size you choose. Running the Cohen's D is just a quick way of saying, nope, sample size is not a factor. We really actually have a true effect size, all right? We truly have some true effect with this type of study. Sample size was not a factor, and that's cool to report. Now, we did also reject. If you reject, that means we should build a confidence interval. Which one? That's up to you. I often do the 95% because it's sweet right in the middle, right? You can do the 90, the 95, or the 99. I like to choose the 95. You should just adjust it if you need to build the 90 or the 99 on your own. 95% confidence interval. Well, a confidence interval captures mu. Because right now we reject it. So we don't believe the mu is 40 for people that move too often. Remember what we're studying. People that move too often. Their level of happiness. It is standardized at 40 points. We believe now, truly, because of the rejection, that the average is not 40. So where is it? That's really what this is where is the average? You now have shown me with 2 tests that the average is not 40. Where is it? And so we build a confidence interval. And this is the formula for the confidence interval. How do I know? It's on my formula sheet. All the letters are pretty clear. X bar, S, and N, those are already known. What is the T value? Well, the T value is based on the picture one more time. A confidence interval is always two-sided. I want 95% confidence, so that goes in the middle, and that's the T. I want the T that bounds the middle 95%. Well, to find that, I use T inverse. And this is what I would do if you're in one of my classes. On your cheat sheet, you're writing little codes of, okay, if Dr. McCullum wants a confidence interval, I use T dot inverse. And that's what it's all about. If I want a critical value, I use T dot inverse. If I want a P value, I use T dot dist. And that's it, guys. You have a little cheat sheet next to you to help you out with this online course. I'm going to put my 975 in here. I'm hoping you realize now why it's 975. Here's a hint. This is 2.5% down here. And the number I put in will always be the area underneath the bar. So, all right, we go to Excel to find it. So I need the T value. That will be T dot inverse. I want 0.975, comma, degrees of freedom. Well, that's N minus 1. Boom. 202 is our number. Sweet. And now that you have the T value, you automatically have X bar, S, and N from your data. Please, if you have raw data, you should be able to find the count, the average, and the sample standard deviation. I hope you know to do that. If you don't know how to do that, go back to my beginning videos on how to find descriptive statistics and X bar and S from a data set. Once you have all those numbers, N, X bar, and S, well, you can build the error. Well, the error is the back part of that formula. The error is T times S divided by the square root of N. That's the back side of the formula in the confidence interval. All right? The error is always this. This is the error, the back part of the formula. And that's what I just wrote into Excel. Once I've got that, the lower bound is your average. I can't state that enough. Your average minus the error. And your upper bound is your average. Remember, this is all about you, your study. You don't believe in the national average, so you got to use your average plus the error. And so there is my confidence interval, 36.44. So my lower bound is 36.44, and my upper bound, what is it? One more time. 37.56. Sweet. From here, I can finally write a nice summary. These are the steps. Now, I may not ask for all of these on a homework or a project or a test, but in research, you really want to do all the details. These are primarily the key details in running a hypothesis test. You run a critical region, you run a p-value, you run the Cohen's d to make sure you have good effect size and sample size is not an issue, and you build a confidence interval only if you reject. I did reject here, and that means I didn't know where mu was, and now I have a better understanding where mu is. I am 95% confident that mu is between those two numbers. I could be wrong, but I'm 95% confident that the true average for people that travel a lot when they were younger, moved around a lot when they're younger, is between those two numbers. Notice the numbers that is not in there. 40. Right? The national average is not in there. Well, we already said that when we rejected that mu would not be in there. So it's kind of like a triple check to me. All right, it's time to summarize everything. First of all, the biggest thing I can say is I reject H0. People are going to want to know, why do you reject? I reject because my T statistic, and you should always report that. Let everybody know your T statistic. What is it again? Your T statistic is negative 10.8. That is in the critical region. They want to see the work? Tell them to look above. This is the summary that everybody reads. When you go to journal articles and read, you read about how people have rejected and what their T statistic is and what their p-value is. Hopefully now you're starting to see, and when you read these journal articles, how it all comes together. My p-value is 0%, and that is less than, how's this, any alpha. In this case, is less than 10%, but it's less than any alpha you throw at me. So that's my p-value. That's why I reject. Since I reject, I also note that my Cohen's d is 1.6, I believe, right? 1.67. And that tells me we have no sample size issues. In case somebody's worried about that, we actually have a true effect in some respects. We also note that I am 95% confident the true average, and it's now time to talk about the problem. We are looking at happiness scales, right? Let's go back to the question. This standardized test is for well-being. The true average well-being score of someone who moves too much is between, and then we report our two numbers again, is between 36.44 and 37.56. And that's huge. We have rejected. What does that mean? We don't believe in the mu. Since we don't believe in the national average for our subset, right? We're looking at people that move around a lot. So bottom line, what is our conclusion? Well, my conclusion is I'm 95% confident the true average well-being score of someone who moves a lot when they're young, too much, I don't think you want to say too much, but moves around more than 5 times, right? That was our clarification, is somewhere between 36.44 points and 37.56 points. Clearly, both of these numbers are under 40 points, which is the national norm. So I'm 95% confident in my work here. And that's all we can ask for. All right, guys. Thank you. Well, hold on. I don't think we're done here. I apologize. We did do A, and we definitely did do B. Can we quickly do C now? So I apologize. So we did a very nice detailed work. This one, we're going to kind of do quickly. So let's say we change from a different from to a more than. Does that change anything? Well, I wouldn't have done a more than here, first of all. My test statistic is a negative, and we believed they would have had a harder time. So if I was hedging my bet, we would have said it would have been less than. So that was a improper question. Less than makes more sense here. And seeing my test statistic, it really makes sense. So let's do a one tail less than test. Okay, a one tail less than test. Well, it doesn't change any of the original information. It doesn't change the test statistic, which is based on N, X bar, S, right? It doesn't change that. What does it change? Well, it does change the critical value. Recall, and this is where what you would do is go back through all the steps. I'm not going to. I'm just going to change the steps that we need. The critical region is changed in a one-tailed test. A critical region in a less than is 1 bar right there. I'm going to put all of alpha down here. Alpha was 10%, so all of alpha goes down here. I want to know the T that represents this picture. That would be a T dot inverse. And that would be a 0.1, because that's the area underneath it, degrees of freedom. And that would be the T value I'm looking for. Again, T inverse says you tell me the area below it, I'll give you the T value that represents that bar. This would be the picture I would replace in my analysis above. All right? We would still go through every detailed step if you're doing the research. I'm just shortchanging it because we did such a beautiful job in the previous part A. Just replace part A, some of the steps. So the critical region, the critical value, the probability is 0.1. Degrees of freedom is 41. So my test statistic, sorry, not my test statistic, I apologize. My critical region now is at a negative 1.3. That needs to be clear. This is at a negative 1.3. Well, that didn't change my conclusion. My test statistic, recall, is still, my test statistic is still hitting at a negative 10.8. It's well within the rejection region, which means I clearly still reject. All right? I still reject H naught since my test stat is in the critical region. All right? It's clear, even though my critical region cutoff is negative 1.3, my value of negative 10.8 is clearly below it. All right? The p-value will change. All right? The p-value, let me think about this. Will the p-value change? Yes, it is one tail. So your p-value will change in this question. Sometimes I need to pause and think about before I say things. So in this case, we're doing a one-sided test. You have your number, and in this case, since we're doing a one-sided test, which is a less than test, all we care about is this area. All right? That's all I care about. Notice there's no 2 bars. That's because we're doing a less than test. A less than test would be 1 bar. So my p-value would not be twice. It would just be straight up the t-dist of that bar, comma degrees of freedom, comma 1. Again, t-dist says, you tell me the bar, I'll give you the probability being below that bar. And that is what I want. So we go to here. My p-value will be equal to t.dist. My test statistic, degrees of freedom, is 41, comma 1. And yes, it's still ridiculously small. It is very, very hard to be under a test statistic of negative 10.8. So my p-value is still 0%, and so I still reject H naught. Conclusion still runs the same for that one. Cohen's d doesn't change, right? Cohen's d doesn't change. It's x bar minus mu divided by s, so that didn't change. My confidence interval, does that change? Nope, right? My confidence interval is based on 95%, so none of this will change. So I still reject, and here's my confidence interval still at 95%. So with a slight little tweaking of the critical region in the p-value, I can redo and do a one-sided test. Conclusions are still the same here. It's not always true that the conclusions will line up, because that test statistic could be close to the critical region. Notice these numbers are close. If my test statistic was a negative 1.5, I would have not rejected here, but I would have rejected here. Notice that. It was a negative 1.5. That is not lower than this number, so I would have not rejected here. But a negative 1.5 is lower than here, so I would have rejected there. The test statistic means so much when we do these tests, all right? The test statistic will tell me if I reject or not. It is a critical component to either the critical region or the p-value approach. Please understand, yes, I reject twice in this case. You don't always do that. Just imagine if your test statistic was negative 1.5. It would have not exceeded this critical value, which means I do not reject. But it would have exceeded this, so I would have rejected in the one-tailed test. So please take your time. That's really my bottom line. Please take your time when you do these hypothesis tests and check all the boxes off. All right, guys, thank you for watching my third video. Stay tuned for more.